solution of problems, because the steps we already discussed. Is it visible to everybody, my screen?
Yes, ma'am.
Yes, ma'am.
Okay. So in previous lecture, we have talked about the design steps, and I have uploaded these steps also in VOLP. I hope everybody has noted down all these steps, and I hope everybody is also everybody has also referred the IS code for relevant clauses which I have written here in these steps. Okay. Somebody has kept the mic on. Can you please mute it? Okay, thank you. So the first step, we have to calculate the ultimate bending moment, shear force, and twisting moment. Then we have to select the suitable size of the beam. And as we discussed in last lecture, that when we design a beam which is subjected to torsional moment, in addition to the bending moment and shear force, we do not consider or we do not provide any separate steel to take care about this twisting moment. Rather, we calculate the equivalent bending moment and equivalent shear force, and for that equivalent values of bending moment and shear force, we design the beam. So in the regular fashion, we have to calculate the longitudinal reinforcement, which we have to provide on the tension side, or sometimes we need to provide the same in compression side also, depending upon the value of the ultimate moment, twisting moment acting on a beam. And then we provide or we design the stirrups for the equivalent shear force. So in the third step, we can find out how to calculate the equivalent bending moment, which is the addition of bending moment and torsional moment. Torsional moment is calculated empty by using this particular formula. Then, if this empty value is greater than mu, that is the bending moment, then we need to calculate this additional moment, for which we provide the area of the steel, or we provide the steel in compression zone also. So obviously, if this value, empty value, is not greater than mu, then we don't need to provide the steel in compression zone. We provide the steel only on the tension side. Okay, so accordingly, appropriate formula we have to use to find out area of the steel. Obviously, whatever the area of steel we are calculating, we have to compare it with the minimum and maximum area of the steel as per the code given criteria. And then shear design, for which we calculate the equivalent shear. The equivalent shear is calculated by using this formula. And then the remaining steps are exactly same, whatever we have learned for the design of shear. So I will quickly go to this. What are the same steps? I will quickly revise those again. We have to calculate the maximum allowable shear, that is tau VUC max, by calculating the tau C max. If VUC max is greater than the equivalent shear force, then it is okay. If not, then we need to resize the section either, or we need to increase the grade of the concrete. Second step is we have to find out the shear force resisted by the concrete. Then we have to calculate shear force resisted by the shear reinforcement and minimum shear reinforcement. And then we calculate the shear force resisted by bent up bars if the bars are bent at the end of the beam, or at the near the support of the beam. Then we calculate the addition of all these three shear forces, that is the shear force resisted by concrete, then minimum shear reinforcement and bent up bar. If this addition is greater than the equivalent shear force, then there is no need to design for shear. We have to provide the minimum shear reinforcement only. If it is not, then we need to design for shear, which is calculated for this value, that is the total shear resisted by the shear reinforcement minus the bent up bars. For this amount of shear force, we design the shear reinforcement, which is provided in the form of a stirrups. So this is a formula which is used to calculate the spacing between the stirrups. So here in this formula, again, we have to take care the impact of torsional moment acting on a beam. So the formula for spacing of stirrups is also a little bit different than whatever we have used for the design of the beams, which are only subjected to bending moment and shear force. Again, the limiting value for this spacing is also different. The first two criteria are same as per the earlier, but the next third and fourth criteria are different for the beams which are subjected to torsional moment. So x1, y1, these are the shortest or shorter and longer dimension of the stirrups. How to calculate them, that we have discussed in last lecture based on this particular diagram. And in this diagram, we also have seen these two additional reinforcement. These two additional bars are provided to the are provided or these are called as side reinforcement. So these are the side face reinforcement. These are provided only when the depth of the beam is greater than 450 mm. If overall depth is not greater than 450 mm, then no need to provide these additional longitudinal bars. And it is calculated as 0.1% of the total cross-sectional area of the beam, and it is provided equally on both the face. Okay. So these are the steps for design of torsion. I hope you have already noted down this in your notebook. Let us start with the problem statement. This problem statement, I don't remember whether you have noted down last time or not. Have you noted it last time? So
No,
just
No,
note
ma'am.
down this
ma'am.
problem statement. Note down this problem statement quickly within a minute. I'm going to read it. A RC rectangular section has following data. Width of the section is 300 mm. Overall depth is 500 mm. Factored bending moment is 80 kilonewton meter. Factored torsional moment is 40 kilonewton meter. Factored shear force is 70 kilonewton. And the materials used are M20 and Fe415. To design the beam if effective cover is 50 mm. So for these values, we have to design the beam. Just tell me once you finish writing of problem statement. I will open the whiteboard and we'll start the solution. Have you finished writing the problem? Okay.
Yes, ma'am.
So let me shift to the whiteboard. We will quickly write down what is the given data so that it becomes easy to solve the problem. So tell me what is the given data. Width of the beam is given. Yes,
Width of section
300
300
mm.
mm.
Then overall depth is given.
Overall depth capital D
Hmm.
500 mm.
The effective cover is also given. Wait.
M20
Effective cover
concrete
is also given. Give me that value first. 50 mm.
50.
So we can immediately find out the effective depth of the beam, which will be 500 minus 50, which is 450 mm. Okay. Then I think mu value is given. What is the value?
80 kilonewton
80 kilonewton
meter.
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 Okay. Then shear force is also given Vu.
70 kilonewton.
Okay. And the twisting moment is also given Tu.
40 kilonewton.
40 kilonewton
Okay.
meter.
Okay, so for this value now we have to design the beam. The first step is we have to calculate the equivalent bending moment. Okay, so I will write down here equivalent bending moment, which is denoted by ME1. So the formula is simply MU plus MT. Okay, we have to find out MT now. What is the formula of MT?
T into 1 plus capital D by B upon 1 by 7, 1.7.
Is it correct? Formula written.
Yes, ma'am.
So put the values. All values are known to us now. TU value is given as 40 kilonewton meter. So I will convert this into Newton mm. So 40 into 10 raised to 6 into bracket 1 plus capital D is 500 divided by B value is 300. Okay, 300 divided by 1.7. So MT is equal to, tell me the value,
62.75.
62.75
0.75 kilonewton meter.
kilonewton meter. Okay. So now let us find out ME1. ME1. So ME1 is MU. What is the MU value? It is 80, right? So 80 plus MT is 62.75. So what is ME1?
142.75.
25.
Yes, kilonewton meter. Okay. Now for this value of the moment ME1, we have to find out the area of the steel which we have to provide in a tension zone or a tension side of the beam. We need to check whether the steel in compression zone is also required, which is checked by comparing this MT value with MU. So MT we have already calculated here. The value is 62.75 and MU is 80. So MT, if it is greater than MU, then and then only we have to provide the steel in compression side. Okay. So here in our case, MT is coming less than MU. Okay. MT is less than MU. So just write down one statement. Provide, therefore, provide steel only on tension side of the beam. Okay. So the next step, we have to calculate now the longitudinal reinforcement. Longitudinal reinforcement, or it is also called as tensile reinforcement. I will write down that also. Tensile reinforcement. The formula of AST is the same one which we have already used for design of rectangular beam. AST is equal to 0.5 FCK upon Fy into bracket 1 minus root 1 minus 4.6. Now here we have to consider the equivalent moment, which is ME1 divided by FCK BD square bracket complete into B into D. Okay. So simply put all the values in this equation. So AST is equal to 0.5. What is FCK value?
20.
20 divided by Fy is 415. 415 है ना?
Yes, ma'am.
Into bracket 1 minus under root 1 minus 4.6 into ME1. ME1 value is 142.75, right? Into 10 raised to 6 divided by FCK is 20, B is 300, and D we calculated as 450 square bracket complete into B into D we have to write down. Okay. So I will simply write down here B is 300 into D is 450. Find out now area of the steel.
1047.8.
1047.8 mm square. Okay. Now check this area of the steel with minimum. So this value should be equal to or greater than AST minimum, which is given by the formula 0.85 B into D upon Fy. So put the values and tell me AST minimum. And we have to also compare it with maximum value. So it should be less than, sorry, it should be less than only, not equal to AST max equal to 0.04 B into D. What is minimum value? AST minimum?
276.50.
283.
5 na? mm square. Okay.
76.50.
Again, sorry.
Ma'am, AST max 6,000 mm square.
Okay. 6,000 mm square. So AST required is well within the range of minimum to maximum. So the same value we can provide. Let us find out now number of bars. For that, let us assume the diameter as let 20 mm diameter bars to be used. So number of bars I can find out here as what is the AST value? 1047.8 divided by area of the single bar, pi by 4 d square.
$3.33.
3.33. So approximately 4 bars. Okay. So if we provide 4 bars, what will be the AST provided? Tell me this value. So it will be simply pi by 4 into 20 square multiplied by 4. Okay. Tell me this value.
1256.64.
1256.64 mm square. And what is the required one? It is just 1047. See, practically when we simply calculate the number of bars as 4 bars and we do calculation for AST provided, whatever is the AST provided, we are providing it. For design purpose, for exam purpose, this is okay. But practically, we must check whether this provided AST is well within the range of percentage steel required for balance section. Why I'm telling you this? Because the value of AST provided is much more higher. See, it is 1256 and the required is 1047. So if required is 1047, we can provide the AST equal to 1050 only. Okay, that is sufficient. If we go on increasing the provided steel, area of the steel in the beam, our beam may turn out as over reinforced beam. So this check is not present in IS code currently in our Indian standard code. That particular check is available in the other codes. Other code means other country codes, that is European code and American code. That particular check is there, but in Indian standard code there is no any check provided to find out whether the provided area of the steel is turning your beam as over reinforced beam. We never design over reinforced beam in practice. Okay, so whatever the AST provided, based on that we can calculate the percentage steel and we can simply compare the percentage steel with the balanced percentage steel or critical percentage steel. Okay, that is a percentage of steel which is provided or which is required for the balance section. Okay, that should be done practically. Yes, it is done. That the percentage of steel based on this AST provided is calculated and it is compared with the critical percentage of steel. It should not be more than the critical percentage of steel. Okay, so for your design purpose, this is okay, whatever right now we are doing, just to understand whether the concepts are clear to you or not. Practically, if suppose based on this AST provided, my percentage of steel coming greater than the critical percentage of steel, I need to reduce the area of the steel. In that case, how can I reduce? See, the number of bars required are 4 as per our calculation. Okay, so instead of providing the same area diameter of the bar throughout the section, we can consider combination of the bar diameters. For example, if I will consider 25 mm 2 bars, I will simply write down here 25 mm 2 bars or 225 plus 1 12 mm bar. Okay, find out the area for this. Okay, so AST will be pi by 4 d square, 2 bars are provided, plus pi by 4, again 12 square, and such 1 bar is there. What is the area? Tell me the value.
1094.85
1094.85 mm square.
mm square.
So this is now sufficient as compared to the required one. The required one is 1047.8 and we are providing 1094.85. So this is perfectly all right. So instead of providing 20 mm 4 bars, we can consider a combination of two different bar diameters like this. We can provide 2 bars of 25 mm and 1 bar of 12 mm. Okay, is it clear to everybody? See, if you consider 16 mm bars, obviously the number of bars required will be more. It may be 5 or 6. So that again we have a restriction to the width of the beam because width of the beam is already given in the problem statement is 300 mm. So in that case, we need to consider the width of the beam also when we calculate the number of bars. Okay, so right now we will continue with this AST provided. Okay, that we are providing now 25 mm 2 bars and 12 mm 1 bar. Okay, so just write down this one sentence. Provide two numbers 25 mm diameter and one number 12 mm diameter bars as tension reinforcement. Okay, so AST provided is already calculated. Just for your understanding, let us calculate the percentage of steel also for this AST. Okay, so percentage steel will be AST upon B into D into 100. Okay, so just find out what is this percentage steel. Use this value, 1094.85. I'll write down your 94.85 into 100 divided by 300 into 450. So what is this percentage steel?
0.81.
0.81 percentage. And if you calculate the same value for this area, I'll simply write down one statement here or. So what is the percentage steel for this area? Quickly calculate. Consider this value AST.
0.93. percent.
Point 93%.
93. Yes, ma'am.
0.93%. See, you can see here the higher percentage of steel is there. Obviously, AST value is more, so percentage steel will be more. Okay, you need to compare this with the balanced one. We have already listed what is the percentage steel for the given grade of concrete and grade of steel. What is the critical percentage of steel that we have already calculated in our fourth or fifth lecture. You can compare this value with that to check whether the given section or the design section. Design means whatever the area of the steel we are calculating, whether it is giving us the beam as under reinforced or it making it as a over reinforced. Okay, this is a practical requirement. We don't expect all this calculation in the examination. Okay, because there is no any clause related to this provided in the code. All right, so we have calculated now the tension reinforcement. We have taken care of the moment now. Let us move to the next point, that is design for shear. Okay, so we have to calculate first the equivalent shear force. So let us calculate the equivalent shear force first.
Ma'am,
Yes.
checking for width we don't have to do for this problem.
Uh, Actually, what will happen if we check for the width at the end we have to check it, because if you consider the last step means for the design of shear we have to calculate the spacing, and anyways there we need to calculate the spacing between the while considering the check for spacing. There are four different criterias now, and for that there we need to calculate the width of the beam. Anyways, you can have that check also here, and based on that we can find out what will be the spacing between the bars of the steel, but you can skip that step here. Okay.
Okay, ma'am.
If you wish, we can do that check here immediately, but that adjustment we need to do once we have to we finish the design for shear also, because we have to find out what is x1 y1, and accordingly we have to make adjustment over there also. So let us complete that step as per your wish. I will consider here. I will erase all this and we will write down check for width here. Check for width. Yes. Truly speaking, Akshata was talking, right? Am I right, Akshata?
Yes, ma'am.
So if you consider here in the problem statement itself, the width is given 300 mm. So we cannot change that width. Though if we are right now checking, considering the check for width, we cannot change the width because it is already given. And for this dimension, we have to find out what is the area of the steel required. And accordingly, we have to adjust the bar diameter. Okay, so let us see, for your satisfaction, we will consider that check. And let us see what happens. Okay, so check for width. What is the formula?
2C1 plus N5 plus N minus 1 C2.
Okay, C2, we have to assume now some value, or simply whatever the, okay, C2 we will assume here. C2 depends upon, C2 is the spacing between individual bars, right? So it depends upon the bar diameter. The largest bar diameter is 25 mm. Okay, and the size of the maximum size of the aggregate, which is normally considered as 20 mm. So out of these two, it should not be greater than maximum of the two value, right? C2 should not be greater than 25. Should not be greater or lesser. What is the clause? I forgot. Should
Should
not
not
be
be
greater
greater
than
than.
25 mm in our case. Okay. So let us assume C2 as 25 itself. Let us assume, I will write down here, let C2 equal to 25 mm. I'm simply write down here as per the clause. As per the clause. I don't have the code kept open here. Can you tell me the clause number, or you can just see?
26.3.2.
Okay.
Ma'am, and actually it should not be less than the greatest.
Should not be less than the greatest. Fine. So it is 25 mm. Na? Should not be less than 25
Yes,
mm. It means. So we have adopted 25. And C1, let us consider as 30 mm side cover. So let us find out now B required. 2C1 plus number of parts are 3 into 5. Now the 5 value we have to consider the largest. How will you consider here? We have to consider the actual values.
25.
2
25.
into 25 plus 12 and 5.
Ma'am,
Uh,
ma'am, there is also one bar of 12 mm.
so I have considered here, 2 bars of 25 plus 1 bar of 12, n into 5. Okay, and n minus 1 here. Now between all the 3 bars, C2 we have kept constant. So this will be n minus 1, 3 minus 1 into C2 is 25. Okay, so check now. What is the required value?
172, ma'am. 172.
Yes, 172 mm, and this is lesser than the actual provided value of 300 mm. So this is okay. Fine. The required value is smaller than. So we have already provided the larger value. So C2 value, C1 value, we can adjust accordingly according to our width value. Okay. So if we consider in this, see in this equation, if we consider instead of V required, if I will consider whatever the provided value 300 mm, I can easily find out what is the C2 value, and we can compare the C2 value with the required one as per this clause. The same thing we did in the earlier problems, right? Because there we can adjust B required. Here we cannot change the provided value. Okay, so I have done in this fashion. So we can increase now C2 in this case also. Is it clear now, Akshata?
Yes, ma'am.
Huh. So C2 value you can increase. Instead of 25, you can increase as per by putting 300 value here in this equation. You can put 300 value and C2 unknown, and you can find out what is the C2. So that will be the provided C2 practical. That will be the practical value. Okay. So let us move to the design for shear now. So equivalent shear force VUE we have to calculate first. What is the formula? VU plus
1.6 TU by B.
yes, TU by B. So what is the VU value? It is 70, right? 70. I have to again convert it into Newton. So 10 raised to 3 plus 1.6. What is the TU value?
40.
T.
Yeah, 40 kilonewton meter, na? So convert it into Newton mm divided by B is 300. So find out VUE.
283.33.
kilonewton na.
Yes, ma'am.
So the next step, what is the next step? We have to calculate VUC max, right? Which is calculated as tau C max into B into D. Tau C max, it depends on, now I need to open code. Without that, it is not possible. I don't remember the page number. Huh? You need to tell me the page number.
73.
Again, please.
73.
73.
73. Okay. Fine. So this is tau C max is table 20. So it depends upon the grade of the concrete. What is the grade of the concrete? M20, na? So
20.
for M20, tau C max is 2.8. So let us write down the value. 2.8 into B is 300 into D is 450. So what is VUC max?
378 kilonewton.
378 kilonewton. This value is greater than VUE, so this is okay. Okay, then the next step, we have to calculate the shear force resisted by the concrete, that is VUC. Okay, what is the formula?
Tau
Tau
CBD.
C into D.
Tau C into B into D. Okay, so tau C value, now it depends upon the percentage of steel. Okay, this is based on table 19. So percentage of steel we have already calculated, which is 0.81%. So for 0.81 means you need to interpolate the value between 0.75 and 1 for M20 grade concrete. Okay, so interpolate the value of tau C between 0.56 and 0.62 and tell me the value after interpolation directly. I will write down the value here directly. Come on fast guys, we are solving one problem only.
Zero 0.574.
Okay. Into 300 into 450. So tell me the value of VUC quickly.
77.54.
Okay. Now what is the next step? Calculation of VUS, which is equal to VU minus VUC, right? So VU is nothing but our VUE value. So I will simply write down here E here. Okay, VU is nothing but VUE, equivalent shear force. So the value of equivalent shear force is 283.33. So this is 283.33 minus VUC we have calculated as 77.54. What is the value we are getting here?
205.79.
Point
79.
79 kilometer. Okay. What is the next step now?
VUSV minimum.
Yes. Formula is
0.4 into B into D.
yes, 4 into 300, 0.4 into 300 into 450.
54.
54 kilometer. Okay. And VUSB, that is the bent up bar, shear force resisted by bent up bars, is 0 because we are not considering any bent up bars in the problem. Okay. So next step, we have to find out the addition of all these three resistance shown by the three different parameters. Resistance to shear force. So VUC plus VUSV minimum plus VUSB. Find out the value. VUSB is
131.54.
1.
31.54.
Yes. Compare this value with VUE, which is 283 if I'm not wrong. Yes, 283. This value is less than VUE, so we need to design the shear reinforcement. Okay, so provide design shear reinforcement. It means whatever the minimum shear reinforcement we provide is not sufficient. Okay, so what is that amount? VUSV we calculate as VUS minus VUSB. Am I right?
Yes, ma'am.
Yes, ma'am.
So what is VUS? VUS is already the calculation of um, this calculation. So 205.79 minus VUSB 0. So it is 205.79 kilonewton, this value. Okay. So let us assume again here, for this shear force, actually we want to find out the area of the stirrups. Okay, so let us assume here 8 mm 2-leg stirrups. So just write down, provide 8 mm 2-legged stirrups. So what is the area? ASV, it is pi by 4 d square multiplied by 2 because there are 2 legs. So what is the area?
100.53.
100.53 mm square, right? Now, yes,
How do we assume that diameters of that bar and numbers?
normally it is 6 or 8 or 10. Practically, the practically used value is 8 mm. So either we provide 6 or 8 or 10 mm, any value between these three.
Okay.
Okay, now the next step we have to find out the spacing. So I will write down the formula for spacing. Spacing between stirrups. So tell me the formula. SV equal to
0.87 into FYS
FYS or
into
FY?
ASV
FYS means uh, uh, FY of the stirrups into ASV
into D1 divided by TU upon D1 plus VU upon 250.
250 or 2.5?
250, ma'am.
Let me check the formula. Where is that formula?
Page 75.
It is 2.5, not 250. See the formula. Am I made a mistake in the PowerPoint presentation? Let me check. Yes. This is 2.5. This is not 250. Make correction in your notes also, huh? This is 2.5, not 250. Okay. Now, what is, I will go back to the code now. What is TU? TU already we have the value, that is a twisting moment. What is B1 here? VU is already known to us. VU is also the shear force acting on a beam. What is B1? B1 is the width, B1 is the center to center distance between corner bars in the direction of the width. Okay, it means if I will consider a diagram of a beam over here, this is my 25 mm bar, the two 25 mm bar and one 12 mm bar. Okay, so what is the description given for B1? B1 is the center to center distance between corner bars in the direction of the width. That means I want to find out this distance. This is B1. Okay, we have already assumed the side cover, right? And don't forget that here the minimum reinforcement will also be there in the top, and I will simply change the color here. This is the stirrups. Okay. So if I will go back to the diagram which we have already drawn here, see here, what is B1? B1 is the center to center distance between the corner bars. Okay, the same is shown over here. So I have to deduct this part. This part means the side cover. Side cover is assumed as 30 mm, right? We have assumed it as 30 mm.
Yes,
Am I
ma'am.
right? Huh.
Yes,
So
ma'am.
B minus side cover is on both the sides. So 30 from this side and 30 from this side. So B minus 2C1 minus half of this bar diameter and half of this bar diameter. So in short, it will be 5 by 2 plus 5 by 2. So it simplify. So the same formula I think I have written over here in the presentation. This formula is there. See here. B1 is B minus 2C1 minus 5. So I will simply write down here the formula of B1 as B1 is equal to B minus 2C1 minus 5. Okay. So B is 300 minus 2 into 30 minus 25. What is B1?
365 mm.
215.
Again, 215.
215.
Okay. B1 we have already calculated. Now what is D1? We'll go back to the code. One more term is here, that is D1. What is D1? Center to center distance between corner bars, and that will be along the depth. This we have calculated along the width. B1 we have calculated along the width. D1 is along the depth. So if I will go back to the diagram here, this is D1. Okay, this is D1. So what is that now? Again, center to center distance between these two bars. So if I will consider this bar diameter, I have to consider that bar diameter. Let us assume the same bar diameter there, or instead of assuming the bar diameter, I can simply find out what is the total depth and I can subtract the effective cover from both the sides. This is the simplest way. Okay, because the effective cover is calculated at the center of the bar from the extreme fiber, either top or bottom. Okay, so what is D1? D1 formula is also written here in this example, capital D minus 2C. So the same I have to write down here. D1 is equal to, this is nothing but D1. This is D1. So capital D minus 2 times C. Okay. So D is 500, right? Minus 2 times effective cover was given as 50. So what is D1?
400.
200. Okay. What else is needed in this formula? Nothing. We have calculated everything. So write down the values, put the values here in the equation. So it is 0.87 into Fy. I will assume 415 only, because we can use the twisted bars also as stirrups. Multiplied by ASV, we have already calculated. What was the value? Area of the stirrups. Guys,
100.53.
100.53. Multiplied by D1, which is 200, divided by TU upon B1. TU value was 40, right? Into 10 to the power 6, because it is in kilonewton meter, divided by B1. B1 is 215. So this is 215.
Ma'am, D1 should be
And D1 is
400.
400, no?
D1 we calculated as
400.
4 or 2?
400.
400.
Ma'am.
Okay. So D1 is 400. Sorry. Okay. So this is 400. Plus VU upon 2.5. VU value was shear force. Tell me the shear force acting on a beam, not equivalent shear force.
70 into 10 raised to 3.
70 into 10 raised to 3 divided by 2.5. All right. So find out SV.
67.83.
67.83 mm. Okay. All right. Now we have to check this value against the minimum values required. Okay. So what is the criteria? SV should be less than
0.75D.
0.75D.
0.75D, should be less than
300.
300, not actually less than. Out of the 4 criteria, whichever is the smallest, it should be less than that smallest value, if I'm not wrong. Okay. So where is the, I will go to the steps over here. Whichever is lesser. So we have to find out all these 4 criteria: 0.75D, 300, x1, and x1 plus y1 by 4. So I will simply write down here smallest of. Okay, 0.75D. What is the value? D is
337.5.
337.5. Okay, 300 is the value. It is already given there. Then we have to find out x1. What is x1 now? X1 is the shorter dimension of your stirrup. Okay, so I will go back to this diagram. This is x1. This is x1. Okay, shorter dimension of the stirrup. We have calculated b1 as center to center distance between two corner bars. Similarly, we have to find out the center to center distance between two legs of stirrups. That is x1. Okay, so we have to simply subtract the side cover from both the side from your total width, minus now half the diameter of the stirrup from one side and half from the another side. So in short, it is phi s, total diameter of the stirrups. So what is the formula of x1 here? B minus 2c1 plus phi s. So I will write down here x1 as B minus 2c1 minus phi s. Okay, so put the values. B is 300, c1 is 30, phi s is 8. Put the values and tell me the value of x1.
232.
232 mm. And second or the fourth value is x1 plus y1 divided by 4. We haven't calculated y1 yet. Okay, so let me do the calculation over here. Y1 is the longest or the longer distance, a longer dimension of the stirrups. So this is y1. Similar to d1, we have to calculate y1. Okay, so this is very simple now. Total depth d minus d dash. If we do, we have to add the area of the bar diameter, half in this direction or half in this direction, plus the half of the stirrup diameter also. So simply capital D minus D dash plus phi s. So what is the formula written here? Or instead of that, we have already calculated D1. We can make use of that. D1 plus phi s. This is the simplest. D1 plus phi s. Okay, so this is the formula of y1. D1 plus phi s. I will
Ma'am,
write down here. Yes.
ma'am, for x1, it should be plus phi s. You've given in the presentation.
Yeah, it is plus or minus. Wait.
Plus, ma'am.
It is plus phi s. We have subtracted it.
So
I'm
then it
sorry.
will come as 248.
Sorry. This is 248, right?
And it should be minus only, no?
Yes.
Ma'am,
Huh?
ma'am, it should be minus only, no? Because we are calculating the distance between the center of two stirrups. So it should be minus.
Let me check the diagram. Whether it is at the center or at the extreme end. As per this diagram, it is at extreme end. As per this diagram, it is at extreme end. So it is not written as center to center. Let me check the clause again from IS code. What was the page number given here?
48.
48. Let me check the clause. Where x1 and y1 are respectively the short and long dimensions of the stirrup. Okay. It is the short and long dimension. It means we have to consider the full length of the stirrup here. So if this is my short dimension of the stirrup, I have to consider the full length. It means it will not be as from center to center. It will be the full. So it is clear that now total width minus the C 2C1. C1 is the side cover plus. Actually, no need to
And then
add
why
anything.
to add them?
C1 is, why to add? C1 is at the center or at the clear, what we have assumed. C1 value, whether it is a clear or at the center we have assumed. It depends on our assumption actually. See, if we assume at the center, C1, what we have considered for B1? B1 we have considered as a clear side cover, right? C1 as a clear side cover, and we added half T. So C1 is a clear side cover. Am I right or wrong? What is the B1 value we have calculated here? As per this formula, B minus 2C1 minus 5. So B minus 2C1 minus 5. It means it is a clear cover. Clear cover. C1 is a clear cover. It is not a center to center distance. That is, the C1 is not measured from center of this bar. So it is at the side of the bar. So C1 is from this edge to the side of the main reinforcement. So in that we need to add now the stirrup dimension. Are you getting my point?
And then we have to add twice the diameter, no?
Twice the diameter. Yes, you're right. So in this case, it will be twice the diameter. Correct. You're right. So x1 will be B minus 2C1 plus 2 5s. That is correct. So let me make the correction here. This is 2 5s. And it is plus or minus?
Plus.
प्लस कसं येईल रे मायनस येणार ना असं का करताय
मेन रेनफोर्समेंट पर्यंत आपण ते C1 घेतलं ना मग पुन्हा आपल्याला x1 पाहिजे ना x1 बाहेर पर्यंत
प्लस येणार ना
हो मॅम प्लस
तू प्लस म्हणलास का मायनस म्हणलास
प्लस म्हटलं मॅम प्लस प्लस 2
ठीक आहे करेक्ट सो इट विल बी प्लस 2 5s
256
एक मिनिट हा So what is this value now? I will simply erase. This is 256.
256.
Now what will be the expression for y1? Is this correct? D1 we have calculated center to center, right? So plus half the diameter of the main bar plus 2 times. Again here it will be 2 times 5s. Wait. Correct. 2 times 5s. Check again. Correct. बरोबर आहे ना आता? So tell me the value now.
$441.
441 mm. Lecture will get extended by 10 minutes, huh? And we have completed only one problem. I plan to complete 2 problems. Okay. 256 plus 441 by 4. What is the value?
174.25.
Okay. So out of these four values, 0.75D, 300, x1 and x1 plus y1 by 4, the smallest value is 256. Okay, so stirrup should be less than 256 and
Ma'am, 174, no?
24.
sorry, one काय झाले मला 174.25. 174.25. So SV should be less than 174.25, which is already there. Whatever our calculated value is already less than. So we can slightly increase the value even. So instead of considering 67, I will go to the higher rounded value of 70 mm. Okay, because it is still less than the smallest value. So just write down, provide SV is equal to 70 mm. Or you can simply write down one statement, provide 8 mm two-legged stirrups at 70 mm center to center. Okay. Now the one more criteria is there as per the steps, that we have to check for the side face reinforcement, whether it is required or not. And what is the criteria? Side face reinforcement. I will simply go to your presentation now. If the overall depth of the beam is greater than 450 mm. Now what is the overall depth of the beam?
500.
It is 500. So it is greater than 450. It means we need to provide the additional longitudinal bars as a side face reinforcement with the area equal to 0.1% of the total cross-sectional area. So you just write down one statement. Since overall depth of the beam is greater than 450, side face reinforcement is to be provided. Side face reinforcement is to be provided. Okay, so ASFR, side face reinforcement, is taken as 0.1%, 0.1% of B into D. So it is 0.1 divided by 100 into B is 300 into D is 500. What is the value?
150 mm. 150 mm square.
Okay. So area on each face, there are two faces, right? So this will be half of this ASFR by 2, which is equal to 75 mm square. So if 75 mm square is the area, we have to find out the bar diameter now. We have to assume the bar diameter. If we consider bar diameter as 8 mm, what is the area of a single bar? Pi d square by 4. Assuming D as 8. Tell me the value.
50.26.
50.26. So that is not sufficient. Let us increase the diameter to 10. Find out pi d square by 4. Pi by 4 into 10 square.
78.53.
So this is sufficient. Okay. So just write down one statement. Providing one number one number 10 mm diameter bar on each face. Okay, so you need to draw the diagram also at the end. So let us draw the diagram. Please use scale when you draw the diagram. Okay, so there are 3 bars. These are 25 mm and the middle one is 12 mm. So this is 25 mm and this is 12 mm. Okay, then we also provide the minimum reinforcement over here. These are also 25 we will consider, and then stirrups are there. So simply show the stirrups. Okay, so this is 8 mm two-leg, and along with that we have to provide the side face reinforcement. No any color available here. Okay, so I will simply draw that by red color itself, the side color reinforcement here. Okay, so these are 10 mm diameter. Okay, and this is provided exactly at the center or between the two reinforcing bar, exactly between the two. So 500 minus 50 on both sides, 400. So this will be half of 400. So this is 200 and this is also 200. Okay, is it clear, everybody?
And the bars in the compression zone, what is the diameter of it?
It is 25. We'll consider 25 only because for x1, y1 calculation we have taken 25 only. Na? Normally, minimum reinforcement we provide in the compression zone. The 12 mm bars are practically provided. So you can show, you can write down here 12 mm also, but our x1 calculation will be different now at the top and at the bottom. So to avoid that confusion, we will consider same bar diameter here. Okay. Is it clear to everybody?
And then this doesn't matter in the over reinforcement. Means it doesn't make the R section as over reinforcement. No.
Over reinforcement, under reinforcement, we decide based on the area of steel provided in tension zone. Okay, we do not consider the steel provided in the compression zone, which is for minimum requirement. That we don't consider in the calculation of AST. Is it clear? Your doubt whether it is clear or
Yes, ma'am. Yes, ma'am.
okay, we will stop here today now. Let me give you the attendance. Actually, I wanted to finish the second problem also, but I think we will have to consider one more lecture to complete the second or third, both these problems. Okay, so on Wednesday's lecture, we will finish now the remaining two problems.